All right, well, it's 5 after, so I'd say Zoom etiquette says we can get started. What do you think?
Yeah, I agree.
All right, so I hit the record button, so it should be recorded. And I know it's kind of small. The screen is kind of small on your end. I'm sorry, I haven't figured out how to best fix that yet. Um, but yeah. All right. So, as promised, you have a lot of pH stuff, which is the stuff we learned last week. All right, so my review starts off with some pH review. Um, so the way I have the practice questions is the same exact wording that you're going to see on the actual test. I just substitute different numbers. So, yes. All right, so what is the hydroxide ion concentration of a solution whose H plus or H3O plus is 1.0 times 10 to the negative 10th? All right, so let me see if I still have my reference sheet in here. Formula sheet midterm. Perfect. All right, so this is what your formula sheet looks like on the midterm, right? You have this acid-base square. Sorry, it's sideways. All right. So we were just given H plus and we're asked to find OH. All right. So we need to use this formula, also known as the KW formula. All right. So I'm going to go back over here. That's the same document. Here we go. All right. So 1.0 times 10 to the negative 14th equals the OH concentration times the H plus. This is hydroxide is OH, right? I don't know. That's my X. Here is my H plus. All right. All right. And so to get X by itself, I'm going to divide each side by this. All right. When I plug it into my calculator, I'm going to make sure I use parentheses. All right. And you should get 1.0 times 10 to the negative fourth. So this would be your answer. Mm. Any questions? All right, I'm going to keep chugging along and you guys just stop me if you have any questions, okay? All right, so question 2 wants to know, it wants to know what the OH is of the sample when you have a pH of 3.34. All right, so I'm going to go back to our acid base square. All right, so they gave us this time pH and they want us to find OH. So finding OH again, but this time we have a little dilemma, right? Because we can't go from here to here, right? There's no step here. So I have two options. Either way is going to be a two-stepper. I can do this formula first, 10 to the negative pH, and then use the KW formula. Or I can find the POH and do the 10 to the negative POH formula. I personally prefer going this way. I think the KW formula is a little messy. So I'm going to first find the POH, right? I'm going to go from pH to POH. So that formula is pH plus POH equals 14. So I have my pH 3.34 plus X equals 14. Subtract 14 by 3.34 to get X by itself. And I get the POH, or X, is, I need to type this in, I don't have this pre-solved. .66. All right. So now that I have my POH, I can go from POH to OH using the formula OH equals 10 to the negative POH. All right, so I can plug 10 to the negative 10.66. Now I can't leave it like this. I have to actually type into my calculator because you can't have decimals in your exponents. As I was grading your guys' labs, that was a common thing I saw. All right, so when I plug it into the calculator, I get 2.18. I could have even rounded that to 19. I probably should. 19 times 10 to the negative 11th. All right. A client with respiratory alkalosis has an H plus or an H3O plus concentration of 5.76 times 10 to the negative fourth in the blood plasma. What is the pH? All right, so again, we're talking about pH. So if I'm taking the test, I'm going to be looking at my acid-base square. So this time they've given us this guy and they want to find pH. So we're going to have to go this way, which is using this formula, pH equals the negative log of the H plus concentration. So pH equals the negative log of the H plus concentration. So we'll go ahead and plug in my 5.76 times 10 to the negative fourth. Okay, sorry. Negative log 5.76 times 10 to the negative 4. I get 3.24. All right, a way to check myself is I want to make sure that my pH is not negative. It has to be positive. It has to be somewhere between 0 and 14, and it should be near whatever my exponent is. So all of those boxes are checked. All right, so that's my final answer there. Number 4, which term best describes a solution with a pH of 3? So just as a reminder, 0 to 6.99 is acidic, 7 is neutral, 7.01 to 14 is basic. So pH of 3 is going to fall in that acidic category. All right. What is the formula of the conjugate base? All right. So if they're asking for the conjugate base, they're telling us that right now this guy is acting as an acid. And when you're acting as an acid, you have a hydrogen that you can give up. All right. So the formula of the conjugate base after it gives up hydrogen would be Cl minus. Because right now HCl is neutral. When we take away one of those H's, it's going to have a positive charge. So we go from neutral to losing a positive, which makes us Cl minus. Usually people have some questions about that. So I have another example here. We have HCO3 minus. So if we're looking for its conjugate base, we're dropping a hydrogen. So it becomes H3OC and then 2 minus. We get even more negative. Any questions? All right, I'm going to keep going.
I'm sorry, I got a quick question. So you saying that the acid gives up a hydrogen, so you'll always take at least one like the hydrogen, that H off?
Perfect. Yep.
Okay.
All right, number 6, they want us to determine the Bronsted base. You don't need to know the Bronsted part. They want us to identify the base. That's what's important on the reactant side. All right. So we have to figure out my first step when figuring out which one's an acid, which one's a base, is to figure out their pairs. What looks similar? To me, I see that H2SO4 looks pretty similar to HSO4 minus over here. They're most likely a pair. H2O looks similar to H3O plus. All right, and so now I'm trying to figure out, where's the hydrogen that's moving? So it looks like SO4 becomes HSO4. So it looks like that's the hydrogen that got lost. And it looks like right here, H2O gains a hydrogen or and becomes H3O plus. All right, so if you're donating the hydrogen, all right, you're an acid. If you're accepting, you're the base. So on the reactant side, on the left side of the reaction arrow, H2SO4 is acting as the base. I'm sorry, H2O is acting as the base. All right. Number 7. So this is something I asked Professor Heck to go over with you guys, calculating weight or percentage weight volume. So the formula for weight volume, and you'll get this on the formula sheet, it's grams over mils times 100. Just so you know that it's on the reference or the formula sheet, let me show you. So on this page, oh, I forgot. I've updated this since uh, I wrote this on here, but percent volume equals grams over mils times 100. All right, so here is my grams. That's great. That's ready to plug into the equation. Here is my liters. So I have to go from liters to milliliters before I can plug this into the equation. So also on the formula sheet is the conversion factor here from milliliters to liters. Okay. So we haven't done a whole lot of practice, if any, but I'm showing you now. All right, so there is 1,000 for every 1 liter. It says there's 1,000 milliliters. So I'm going to take this 0.34 and times it by 1,000. That will get me 340 milliliters. All right. So now I have my grams and my milliliters. I can plug it into this equation. All right, so I have my 2.3 over 340 times 100. Let's see what this says. 2.34. Sorry, 2.3 divided by 340 times 100. I got 0.63%. All right, number 8. Normal saline solution is used for IV drips. It contains 1.12 grams per zero point 0.7 liters of solution. What is the molarity? So molarity was another topic that you would have went over with Professor Hecht. Molarity, also known as big M or capital M, is moles over liters. And this should be on your formula sheet as well. Let me just go back and confirm. Yep, right here. All right. So in this problem, they gave us grams and liters. So kind of like the last one, they've given us half of the equation that's ready to plug in, but not quite. So we first have to go from grams to moles. Oops, that's really ugly. Right? So this is taking us back to like lecture 1 and 2 a couple weeks ago. All right? So in order to go from grams to moles, or even vice versa, we need the molar mass. All right? So I've already got this one pre-solved for us. The molar mass of NaCl is 58.44 grams per mole. All right? So I'm going to set this up 1.12 grams. All right, on top, I want my grams on bottom so that way they cancel, and my moles on top. This number, 58.44, travels with the grams, so since I put the grams on bottom, I'm going to put that number on bottom. It's going to cancel out my grams and leave me in moles, which is what I want to be in. All right, so I'm going to do, in my calculator, 1.12 divided by 58.44, and I get 0.019 moles. All right. So I've boxed a lot of things, but let me go back over it. So I have my liters, and now I have my moles. So now I'm ready to put these two things into this equation over here. All right. So I got 0.019 moles over 0.7 liters. And it's just a matter of putting this into the calculator. You get 0.027. We're solving for big M, or molarity. And so my final answer, I have so many things boxed here. Final answer, 0.027. All right.
Are
Part
we are I'm sorry. Are we getting calculators like on the computer, or are we have to bring the one that we're supposed to have?
there will be a calculator embedded in the testing program, but I encourage you to bring your own calculator.
Okay.
All right, 9. A gas mixture of neon and argon has a total pressure of 1.7 atmospheres. The partial pressure of neon is 0.89 atmospheres. Calculate the partial pressure for argon. So this was another one. These next few are ones that you would have went over with Professor Hecht. So the partial pressure law is that the pressure of the total is equal to the pressure of the part, or partial. That's why it's called the partial pressure law. So this could be it for 2 gases. This could be for 5 gases. Here it's 2. So they're telling us that the total is 1.7 atmospheres. And then the 2 partials would be the neon and the argon. So we don't know what it is for argon, but they do tell us for neon it's 0.89 atmospheres. And we need to solve for what it is for argon, which would be x. All right, so to get x by itself, we'll subtract each side by 0.89. So 1.7 minus 0.89 equals 0.81 atmospheres. That would be your final answer. All right, and if you forget that formula, it will be on your reference sheet. So gas law is up here. Dalton's partial pressure. So it just says that the total is equal to, if you had 3, if you had 4, if you had 5, you can keep it going. All right, number 10. In the laboratory, a student dilutes 34.5 milliliters of a 2.75 nitric acid solution to a total volume of 300. What is the concentration of the diluted solution? So we're using the word diluted, so you want to use the dilution equation. All right. So if you forget what the dilution equation is, you can go over to your reference sheet. Here it is. It's written on here right now, but on the final one, it's typed in there. So the dilution equation is C1V1 equals C2V2. And so let me rewrite that over here. C1V1 equals C2V2. All right, so basically you just have your concentration and your volume before, and then your after. All right, so they're telling us that a student dilutes 34.5 of 2.5. So to me, that's reading as volume 1 is 34.5 milliliters. Concentration 1 is 2.5. This is my before. And then they're saying my total volume, so my after basically is 300 milliliters, and they want to know what is my concentration after the dilution. All right. So I have all my variables but one. All right, so it's time to plug them in. So C1, 2.75 times V1, 34.5 equals C2 is my X times 300. Divide each side by 300. So in my calculator, I'm typing 2.75 times 34.5 divided by 300. And so X, or C2, is 0.316. All right, still doing okay? All right, 11. All right, a 3.5 mole sample of gas is confined to a 6.75 liter tank at a temperature of 25 C. What is the pressure in atmospheres? All right, so there's a lot of stuff about gases and stuff. So if it says partial pressure, that's when you use the Dalton's partial pressure law, which we just did in 9. Okay. If it has the word dilution, you're using the dilution equation that we did in 10. Molarity, you had that equation in, 8. Here, they're not really telling us, they're not giving us a clue to what equation it might be, but they're giving us a lot of variables. All right. And they're talking about a gas. So something that talks about a lot of variables and references a gas is this first law up here called the ideal gas law, where PV equals nRT, and R is a constant value of 0.0821. All right. So that's what 13 here, I'm sorry, 11 is referencing. This is the ideal gas law. We're talking about gases still, but they didn't really define. They gave us a lot of variables, so we're thinking the ideal gas law. All right. So again, ideal gas law, PV equals nRT. So P is pressure. Okay. So it has to be in atmospheres. That's how this equation works. But as the problem states, that's what we're trying to solve for. V is volume, 6.75 liters. So I'm getting that from here. N is the number of moles. So again, I'm getting this from the problem, 3.45 moles. R is that constant that you're given on the formula sheet. I'm running out of room. T is temperature. The thing is, temperature has to be in Kelvin for this equation. And they give us temperature in Celsius. So just like some of these other problems, we have to convert first before we can plug it into the equation. So a reminder, Kelvin is Celsius plus 273. That's again on your reference sheet. I'm not going to go back just to save some time because we do have some other temperature converting ones that I can show you where that formula is. So to find the Kelvin, I need to do 25 plus 273, which is 298. So that's what I want to plug into my equation. All right. So P is my X, V 6.75, N 3.45, R 0.821, T, I'm running out of room, 298. All right, so to get X by itself, I'm going to divide each side by 6.75. And when I do this and plug it into the calculator, 3.45 times 0.0821 times 298 divided by 6.75, I got 12.5. And this would technically be in atmospheres, ATM. All right, 12, a client has a systolic blood pressure of 375 millimeters mercury, and we need to express this in atmospheres. All right, so we just need to do our good old conversion method. We just don't know the conversions. And of course, we can find that on the reference sheet. So here is the conversion. 1 atmosphere equals 760 millimeters mercury. All right, so I'm going to start with what I'm given, 345 millimeters mercury. I'm going to set up my little T here. All right, millimeters mercury on bottom because I want them to cancel, atmosphere on top. So it was 1 atmosphere equals 760 millimeters mercury. So 1 on top, 760 on bottom. So in my calculator, I'm typing 345 divided by 760, and I have 0.45 atmosphere. All right, so that covers the gas law stuff. Now we're moving into stoichiometry, which is what I reviewed with you guys at the end of lecture 2. All right, so you have 2 stoichiometry problems. You know that there's stoichiometry when you're given a balanced equation already. So 13 and 14 here are stoichiometry problems. All right. So stoichiometry, this is when we're going back and referring to, where'd I put it? Right here, this map. All right. So sorry I can't turn it unless there's a button I'm missing, but so you'll have to look at it sideways here as we go back and forth. All right, so 13, given the following equation, determine how many grams, we're trying to figure out how many grams FFE are produced from 4 moles of Cl2. So that's my start. 4 moles of Cl2, and I need to get to grams of Fe. All right, we're going to go back to that map to give ourselves a little refresher on what the heck we're doing. All right, so I'm starting with moles of a reactant, and I'm trying to get over here to grams of the product. All right, so it looks like I have two steps. First step is using the mole to mole ratio from the balanced equation to go from moles of a reactant to moles of a product, aka switching substances. And then the second step would be to use that molar mass to go from grams of the iron to, I'm sorry, to go from moles of the iron to grams of iron. All right, so step one, using those mole to mole ratios. So right now I'm in moles of Cl2 and I want to get out of moles of Cl2 and into moles of Fe. All right, so for every 3 moles of Cl2, there are 2 moles of Fe. All right, so 3 moles here, that's where I got that, 2 moles here. So now I'm out of moles of Cl2 and I want to get to grams. And put moles of Fe on bottom and grams of Fe on top. All right, so whenever I'm going from grams to moles, that's using the molar mass. And so since it's just a single element, I can just find that on the periodic table. I forgot to look this one up, so I'm going to real quick do that. The molar mass of Fe, or iron, is 55.85. All right, so 55.85 for every 1 mole. So now I'm out of moles of Fe and into grams. All right, so in my calculator, I'm going to do parentheses 4 times 2 times 55.85, close parentheses, divided by 3. All right, and so I got my final answer, 148.9 grams of iron. Any questions? All right, 14 is similar. How many moles of FeCl3 are produced from 0.35 moles of Cl2? Here, this one's just a one-stepper. We're just going from moles to moles. So we just need to mimic that first step we did in the last problem. All right. So we're going to start with 0.35 moles of Cl2. And since I want to get out of moles of Cl2 and into moles of Cl3, I'm going to put that on top. All right, so I have 2 moles. Oh, no, wrong thing. I have 3 moles, because that's the coefficient for Cl2, and then 2 moles of FeCl3, because that's the coefficient for Cl3. All right, so now I'm out of moles of Cl2 and into moles of Cl3. So in my calculator, I can do 0.35 times 2 divided by 3. And when I do that, I get 2.33 moles of FeCl3. Questions? All right, 15 is balancing. All right, so we talked about balancing back in lecture 2, I believe. So I taught you guys to draw a line down where the reaction arrow is, list each of the elements in the same order on both sides, and to start by doing an initial count. So on the left side, I see 3 carbons, 8 hydrogens, 2 oxygens, and then on the right side, I see 1 carbon, 2 hydrogens, and 3 oxygens. All right, tricky stuff. It's all trial and error. I think I'm going to start with putting a 4 in front of the H2O. When I do that, I'm now multiplying this 4 by this little 2 to get my total number of hydrogens. So that brings my total number of hydrogens up to 8. It also takes my 4 and multiplies it by the implied 1. So now I have 4 oxygens just from the H2O. I still have my 2 oxygens from the CO2. So that brings me up to 6. Oops, that's not what I want. All right. Now I have my hydrogens balanced. I'm thinking maybe I'll put a 3 in front of this. That will bring my carbons up to 3. It's also going to add more to my hydrogens or my oxygens again. So again, we have 4 oxygens from the H2O. And then we have now 6 oxygens from, this looks like 40 and 60. I meant to say oxygens. 4 from the H2O, 6, 3 times 2, this 3 times 2, 4 from the CO2. So now I have my 6 plus 4. Now I have 10 oxygens. So my carbons are balanced, my hydrogens are balanced. My oxygens are not balanced, but I'm in a good spot. If I put a 5 here, 5 times 2 is going to equal 10. And that will balance them without changing anything else. So that leaves me at my final point. All right, questions. All right. 16. A nursing student has a sample of methane gas, CH4, containing 3.1 times 10 to the 19th molecules. How many moles of CH4 are in this sample? All right, so we're trying to go from molecules to moles. All right. So if we go back to this formula sheet, we go back to this map here. All right, so now we don't have a stoichiometry. So basically we can just cross off this side, one side, all right? What we're trying to do is just look at this. What's the relationship when we're not working with a balanced equation, okay? So we have we have molecules, which is the same as particles, right? We said we could enter stuff for this last thing, and we're trying to get 2 moles, right? So that means I need to use Avogadro's number, all right? And if you forget what Avogadro's number is, it is right here, all right? So all right, so Avogadro's number says that 1 mole equals 6.02 times 10 to the 23rd molecules. All right, so now that I know that relationship, I just need to set myself up with my little t-chart here. So I'm going to start with what I'm given, 3.1 times 10 to the 19th molecules. I'm going to put molecules on bottom because I want them to cancel. I'm going to put moles on top. So that leaves me with 1 mole on top and then 6.2 times 10 to the 23rd on bottom since it's Avogadro's number. So I got my molecules to cancel, and then my moles are on top, which is what I want. When I go to plug this into my calculator, I want to make sure that I use parentheses. So I'm going to be doing open parentheses, 3.1 times 10 to the 19th divided by open parentheses, 6.02 times 10 to the 23rd, close parentheses. All right, I don't have this ready to go, so just give me a second. Oh no. One sec. Typed it in wrong. All right. I got 5.14 times 10 to the negative 5. All right, 17. All right, so 17 is a little weird. So a student has 4 moles of C3H8, and we want to know how many moles of hydrogen there are. All right, so now we want to go from moles of C3H8 to moles of oxygen. The last time we switched substances, we had a balanced equation and we were doing stoichiometry. If you're trying to switch substances and you don't have a balanced equation, then you are using the subscripts from the formula itself. But I'm going to show you how to do that here. Okay. So like most other problems, I'm going to start with my T-chart. I have 4 moles. Oops, let me say 4 moles of what? C3H8. All right. So for every 1 mole of the entire molecule, you have 8 moles of hydrogen. All right. And I'm getting that because C3H8, there's 8 hydrogen in 1 molecule. All right. So I can cross off that. All right. And now I'm into moles of just hydrogen. And so 4 times 8 is 32. So my answer here would be 32 moles of hydrogen. Okay, I'm gonna keep going. So 18, looks like we're going from moles to grams. So we've already done this already. It's just another practice here. So to go from moles to grams and vice versa, we need the molar mass. All right, so the molar mass of water, or H2O, is 18.02 grams per mole. All right, so we're going to start with 0.45 moles. I'm going to set up my T-chart. I want moles on bottom because I want them to cancel, grams on top. The 18.02 is married to the gram, so since I put the grams on top, I'm going to put him on top. And then I'm going to put 1 mole on bottom. So I've canceled out my moles and I'm into grams. And so I just need to multiply 0.45 times 1802. I got 8.011. Yeah, I'm around that. 8.11 grams. All right. 19. We are given a nuclear symbol here, and we are asked to find the number of protons, neutrons, and electrons. All right. So the protons in our symbol, this is the bottom left number always. All right, so protons here is 35. We can get that directly from the symbol. Neutrons, that's when you do the neutrons. So when you do the top minus the bottom. All right, so 80 minus 35, which is, what is that, 45? 70, yeah. So neutrons is 45. Electrons. So if there's no charge in the top right, then the protons equal the electrons. But here in the top right, we have, it looks like a charge of -1, which means we have one more electron than we do proton. We're more negative. So we have 36 electrons. Okay, that would make me one more negative. If I'm minus, I have to have more electrons than I do protons. All right, 20, find the molecular weight or the molar mass. Those mean the same thing. All right, so I've been solving these for you. And on the test, I'm gonna give you on your reference sheet, you're gonna have a box of them, except for one where you have a test question that looks like this, where it's testing your ability to calculate a molar mass, and that one I'm not gonna give you on the test. You have to know how to be able to do it. So in order to calculate a molar mass, we need to add up all of the individual masses, all right? So I have barium, I have chlorine, specifically I have 2 chlorine, so whatever my molar mass is, I need to times it by 2, and then I need to add these together to get my total, all right? So I'm going to find this from the periodic table. I don't know if I have a periodic table in my little notes here. I don't think I do. So I'm going to go to the periodic table. I'm going to go to Google real quick. Barium Ba. Where is Ba? Oh, here it is. Okay, it has a molar mass of 137.33. And then chlorine has a molar mass of 35.45. All right, so I'm going to take 35.45 times that by 2. All right, I get 70.9. I'm going to add that to my barium, 137.33. And I got 208.23. All right, so that's how you calculate the molar mass. All right, 21. This brings us back to our temperatures. We've already used temperatures in, that other problem, the ideal gas law problem, but here we're just straight up converting temperatures. All right. So they say that a temperature reading of 75.1 degrees is measured with a Fahrenheit thermometer. What would this reading be in a Kelvin? So we need to do 2 steps here because we don't have a formula that goes from Fahrenheit to Kelvin. Maybe there is one out there, but on your formula sheet, you're going to have Fahrenheit to Celsius and then Celsius to Kelvin. All right, these are from the reference sheet. I just left them there so I didn't have to come back and copy them. All right, but they are on that reference sheet. So to go from Fahrenheit to Celsius, here's that formula there. 5/9 times 5, or I'm sorry, Fahrenheit minus 32. So 5/9. Here it says it's 75.1 minus 32. So I would type in my calculator 75.1 minus 32, close parenthesis. What is going on? Oh, don't put a parenthesis if you didn't start with one. Okay. So in my parentheses, we got now 43.1. So now I want to times that by 5/9. and I got 23.9. And so now that's my Celsius, I need to add that plus 273 to get my Kelvin. And I got 296.9 as my answer. All right, 22. Got a lot of weird wording here, but if you see the word density, this is the setup you're going to do. All right. And remember, these questions are mimicked after the test. I just changed the numbers. So when you see density, this is what you want to do. All right. Ethanol, ethyl alcohol has a density of 1.23 grams per mil at whatever temperature. When you see this problem on your test, you don't care about the temperature. Black that out so it doesn't confuse you. All right. If 80.1 grams of ethanol is needed for the reaction, what is the volume in milliliters? So they gave us that we're starting with 80.1 grams of ethanol, and we're trying to figure out milliliters. Okay. So we want to do our T-chart, right? We want to start with what we're given. All right. And then this is the conversion factor we're going to use. Okay. So grams on bottom because I want them to cancel, milliliters on top. So I have 1.23 grams for every 1 milliliter. All right, so I'm going to do 80.1 divided by 1.23. All right, so 65.1 milliliters. All right. 23, we're working our way back to that first lecture. In fact, I think temperature was part of that first lecture. That's where we worked our way back to that first lecture. 23, we want to identify the number of sig figs. All right, so you have, I believe, 2 problems where you have to identify the number of sig figs. All right, so I gave you 4 examples here just for extra practice. All right, so just a reminder, leading zeros never count. Sandwiched zeros always count. And it's the trailing zeros that are weird, all right? They only count after a non-zero and a decimal. All right. So, right, let's see. How do I want to do this? Okay. So we have 2.001. So of course the 2 and the 1 are going to count because they're non-zero digits. And then our zeros here are sandwich zeros, so they're going to count. So that leaves us with 4 sig figs since all of them count. For the next one, the 2 and the 1 are going to count. This 0 here that I just highlighted is a sandwich 0, so he's going to count. But those first 2 are leading zeros, and they're not going to count. So that we have 3 sig figs here. Third one, the 2 and the 1 are going to count. The 0 between the 2 and the 1 are going to count as a sandwich. Now, we have a trailing 0. It's trailing after a non-zero digit, but there's no decimal. All right, so it means it doesn't count, and you have 3 sig figs. We don't need to do this example. I don't think you see that example on the test. All right, 24. So again, you're going to see about 4 examples where you want to write names of the compounds. So I gave us like 6 examples here. All right, so the first step in these, though, don't forget, is figuring out if it's ionic or covalent. All right, so as a reminder, ionic was between a metal and a nonmetal. Covalent is between two nonmetals. All right. So I'm just going to go down first and identify. So nitrogen and oxygen, those are both nonmetals. They're on the right side of that stair step. So this is a covalent compound. Carbon and oxygen, both nonmetals. So this is covalent. Carbon and oxygen, again, just in a different ratio. That's covalent. Hydrogen and oxygen, both nonmetals. This is covalent. Magnesium and chloride. This is ionic. Magnesium is a metal. Potassium and chloride. This is also ionic. Potassium is a metal. All right. So if it's ionic, that's when I get to just say the name and add "ide" to the second one. But if it's covalent, that's when I have to do the prefixes thing with the numbers. All right. So N2O6, since it's covalent, I need to say what those prefixes or say what those numbers are with prefixes. If you forget what your prefixes are, they are on the formula sheet here. All right. So we have dinitrogen, di because there's two. 6, oof, I'm blanking on 6. Hexa oxide. CO, carbon monoxide. So subscripts of 1 was the weird one. So if they have coefficients of 1, you leave mono off the first but not the second. CO2, carbon dioxide. H2O2, dihydrogen dioxide. All right, now we're to our ionic compounds, which we don't have to state the numbers, so I'm just listing that first element, magnesium, and then listing the second element, but changing the ending to "ide." So magnesium chloride for MgCl2, KCl, potassium chloride. All right, any
Are
questions?
we are we gonna have to know like if it's high to low or any of that like we did on the owl?
High to low. I don't know what you mean by that.
So you know how we had like the ionic bonds is high to low on the periodic tables? I think that was in like the first lecture.
I'm not familiar with calling them high to low. I periodic trends. There was like atomic mass and ionization energy.
Yeah, yeah.
Yeah, those are on there. Those are actually coming up down
Okay.
here, I think, somewhere. Oh, we still have so many more. Ah, okay,
Okay.
we got this. I got this. All right. So 25, what would be the chemical formula for calcium and iodine? So this is where you have your periodic table, right? And I told you guys to write the trends on here for like +1, +2, +3, skip a few, +-4, -3, -2, -1. All right. So calcium is a +2 and iodine is a -1. So you flip the charges. So we have CAI coming together. So the 2 is going to go with the after the I, and the 1 is going to come after the calcium, but we don't really write out ones. So the chemical formula would be CAI2. pH buffer, I'm going to skip this one because you just had to write this in your discussion post, and that basically explains it. All right, 28. I have a slight typo. C should be option should be low OH. All right. This is a pH question that I snuck back in here. So 8 is on the basic side of the pH scale. So if something is basic, it has more OH than it does H plus. All right. So it would not have high H plus. It would not have low. I'm sorry, it would have low. It would not have low OH. It has high OH. All right. So you could categorize it as having low H plus if it was basic. Particles that are too large to pass through the dialysizing membrane. You guys also wrote this in your discussion post, but colloids. All right, if two liquids completely dissolve in each other, they are soluble or miscible. Saline solution is NaCl and water. So solute is what is being dissolved. So in this case, NaCl, and the solvent is what's doing the dissolving. So in this case, water. All right, the states of matter. We have 3 states of matter: solid, liquid, gas. All right, so the one with indefinite shape but definite volume would be liquid. Think about if you had a certain like volume water bottle, but you dumped it on the floor, right? It's still that definite volume, but it's changed shape. Definite shape and definite volume is going to be your solid. And indefinite volume and shape is going to be your gas. Gases, they take on the shape of their container, but you can also compress them. All right. Which side are the reactants on? All right, so just a reminder, you have A plus B yields C plus D. Your reactants are on your left side, and your products are on your right side. You're going to see 2 questions about that, so hopefully those are easier ones. Exothermic and endothermic. I can't remember if we talked about this. All right, so exothermic is when heat leaves a reaction or it's on the product side. Oh yeah, we did talk about this. So heat leaves, so it's exo, heat exiting, endo, heat going in, so heat entering, and heat's on the reactant side. Reduction, we just need to know the definition of it, and it's when you are gaining electrons. All right, classify the following reactions. We're just going to do 2 of them. All right, so we have, just a reminder, when we have A plus B equals AB, they come together. This is called combination. When you have AB, then it turns back to A plus B. This is decomposition. When you have A plus B, C yields AB plus C. This is single replacement, where you got somebody single on both sides. And then when you have AB plus CD, changes to AC plus BD. This is your double replacement. All right. So number 1, I see a double replacement. We got a lot going on here. We got PB with Cl2, Ag with NO3. Now PB is with NO3 and Ag is with Cl, so they swap partners. NH3 plus HCl coming together to form one thing. So I see combination. 3, I also see that double replacement. We got Al and Cl together, then we have Na and SO4, then we have Al, SO4 coming together, and NaCl coming together. All right, simple ion of iodine. So again, this goes back to the +1, +2, those things on your periodic table. So iodine is a -1. Electrons in the outermost shell, so your valence electrons, again, this is something I told you guys to write on your periodic table. So this was just your 1, 2, 3, 4, 5, 6, 7, 8 thing. And so magnesium's in the second column, so it would have 2 valence electrons. All right, how does the periodic trend for ionization work? So if we imagine the periodic table, the trend increases as we go to the right and increases as we go up. And so you're going to see this in words. So increases right, increases upwards, something along those lines. As long as you have it written down on the trend on your periodic table, you should be good. Atomic size, this is the one where you have to list the elements in the order. Atomic size is the opposite trend. So if this is the periodic atomic size, it increases or it decreases as you go down and to the left. So I believe fluorine is the biggest, and then chlorine, and then bromine. Oh, I'm sorry, I'm listing this backwards. The biggest would be AT. Then it would probably go, I gotta look at the periodic table, but I'm pretty sure fluorine's the smallest, AT is the largest. Let me see, I gotta look at a periodic table. Yeah, so AT, from all these elements that I listed, AT is closest to the bottom. Then it goes Br, and then Cl, and then fluorine is closest to the top, which would be smaller in terms of trends. All right, characteristics of metals and nonmetals. So if we have our stair step here, metals are over here, nonmetals are over here. This is a periodic table. All right, nonmetals are malleable. No, I'm sorry, they are not malleable. They are nonmetals. They're typically gases at room temp. They are poor conductors of heat and electricity. Metals are malleable. They are typically solids at room temp. And they are good conductors of heat and electricity. All right, elements located in period 4, group 2. So again, you have to just kind of do that little search on the periodic table. So period 4 is, group 2, calcium? No, group 12. So period 4, group 12, zinc. All right, zinc. All right, the decimal number, that's the molar mass or the molecular weight. All right. So solution is when you have two or more substances together. So you can think of that NaCl and water, that saline solution. Matter is anything that has mass and takes up space. Mass is basically weight without gravity, or the amount of space something takes up. And element, that's just what's on the periodic table, right? Chemical properties, this is going to be like rusting or baking a cake. Physical properties are going to be like changing color. All right, and then term that best describes CO2. So this refers to the like atomic stuff where you can be monoatomic, diatomic, triatomic, or polyatomic, right? This refers to the number of atoms that you have. And then you can be homoatomic or heteroatomic. So homo, those atoms are alike. Hetero, those atoms are different. So here H2, or I'm sorry, CO2, there's 3 atoms here, so this would be triatomic. And then those atoms are different. We got carbon and hydrogen, so they would be heteroatomic. So it's a triatomic and heteroatomic molecule. All right, that's finally the end. Any questions? All right, if there's no questions, I'm going to end it so I can start getting that recording loading.